Hello people, this is Pradeep Vibhuti. Let us see basic operation of FET and also biasing. So operation in our previous video we have already seen. Nevertheless, we'll see much more in detail because we are adding some other conditions for this. So this is the FET. We have P type material and we have two N type material. And as you can see, gate is connected to both P type only. And as you can see, one of the N side is connected to VDD, that is drain, and another side N is connected to the source. So for source we have connected it to ground, and as I said, between two N channels we have a path. In fact, you can see this is a single N material where one side of N material is connected to the drain, which is given to the positive VDD. The negative VDD, which is given to the source, is connected to the other side of the N type material. And electrons will flow from N to N, that is source to drain. So since electrons flows in upward direction, current ID, which is equal to IS, flows downwards, and that current becomes IDSS when VGS is 0. So whatever the current flows for VGS is equal to 0 volt condition, then that current we call it as IDSS. Now for this diagram, VP is 6, so pinch off voltage is 6. This diagram, in the sense, for this dimension of FET, VP depends on the dimension. So for VGS is equal to 0, we always get IDSS, fine. And when VP is equal to 0, IDSS is 0. So for different VP, that is VGS, okay, -1, -2, -3, as we have discussed in our previous video, okay, we get values and these values are been joined. And you can see here we have an Shockley's equation. Based on that, these values are marked. So that equation will come to know later, Shockley's equation. And as we have seen this diagram here, for VP is equal to VGS, which is equal to -6, we don't have AD current, but for all other conditions between -5 to 0 we have certain amount of current, and the locus of VP, that is pinch off voltage, goes like this, which we have seen in our previous video. Now let us see the biasing configuration of FET. So what is biasing? Biasing is nothing but setting up an initial conditions before you give some signal to amplify. Suppose you want AC signal to be amplified, you just have to bring it, the FET device, in an active condition. So for example, here is an AC input and here you have AC output. So in order to amplify this, okay, you need to first bring this into active state, make it available for operating conditions. So to make it to be available or ready for operating, okay, we need to do some biasing. How that biasing is done? We have different biasing. So firstly we will see fixed bias configuration. Fixed bias in the sense we are giving a fixed voltage. So since we are giving a fixed voltage, the analysis is simple for this. Here very particularly we must know that these capacitors are coupling capacitors. This is input coupling capacitor, this is output coupling capacitor. So if input is AC, this capacitor will come into picture because it will continuously charge and discharge. But for biasing we do the analysis for DC. So for DC these are open circuit. It means whatever you give the input doesn't matter, because capacitor, once it is fully charged, it doesn't charge, right? For DC initially it will charge, after that it doesn't charge. If it is not charging, it means it is open circuit. So for DC analysis we consider it to be open circuit. Yes, it is written here. And the RG here, what we are seeing, since this is a very low voltage, very low current will come. Since very low current, the drop here is very less, which is Vg, which is nothing but Ig into Rg. The drop is so less that you can neglect it. Since there is no drop, it means it is almost 0 volts. If it is almost 0 volts, you can consider it as a short circuit. Correct? Almost negligible current. So almost no voltage. If there is no voltage across Rg, you can consider it as a short circuit. So the circuit diagram becomes something like this because capacitor is open, as I said. So here also capacitor is open. You should always know that. I repeat it again. Capacitor acts as open circuit for DC and short circuit for AC. So since we are doing DC analysis, we have just opened it up. So since they are open, input and output doesn't matter. So you are just making it ready for operating. That is called as biasing. Now, this is the equation. So before going that, we'll see what is this equation. See here. So the circuit becomes like this once capacitors are opened. We neglect it because it is creating an open circuit, so it doesn't come into picture. So circuit, equivalent circuit becomes this. Here you can see that Vg now is the only source in this circuit. True, because these two are grounded, so both are same potential. You just join it. Correct? So this is the circuit. In this circuit, this is the only source, and obviously there is a drop, just like in BJT. Correct? There, here it is base, here it is emitter. VBE is nothing but VGS in this FET. So what happens, whatever the voltage is produced here will have to drop here. That is this VGS is nothing but opposite to that, because here you are entering positive and here also you are entering positive. So both are with a minus sign. This is the convention for KVL. So these are the only two voltage drops which is equated to 0. This is the KVL applied for this loop, and it yields to be VGS is equal to minus VGG. So VGS is opposite of this. Now, having said that, we have got this. This is the equation what you need to remember to calculate ID. So this is the equation given by Shockley's and called as Shockley's equation is ID equal to IDSS into 1 minus VGS by VP whole square. As I said in our previous video, IC is equal to beta IB. This was the equation for output current. IC was considered to be output current and this was the controlling current, and the relation was beta. But here this is a linear relationship. Since FET is not a linear device, it is a non-linear device, so we have a non-linear equation. Square makes it non-linear. You can just see here it is non-linear. So this is the equation here can be used for graphical analysis as well as mathematical analysis. We'll see both. Now in this equation you substitute VGS is equal to VP, VGS equal to 0, okay, and VGS is equal to VP by 2. In this equation you will get these values. So here VGS is equal to VP. What happens? 1 minus VGS by VP is same, so it becomes 1. VGS is equal to VP, right? So VP by VP is 1. 1 minus 1 is 0, so ID becomes 0. Similarly here VGS is equal to 0, right? So this is the VGS axis. Here it is 0. If it is 0, okay, 1 minus 0, so it becomes IDSS. IDSS into 1 minus 0 is IDSS into 1, which is nothing but IDSS. You get this point. So similarly you substitute VGS is equal to VP by 2. Yes, you will get IDSS by 4. You can try it. You can substitute and try it. Now we will be operating at VGS at some minus VGG, yes, some voltage. So once you draw a straight line which intersects the device characteristics, with the network characteristics, we call it as a Q point, and that corresponding to ID will give us the operating current. Fine, it is as simple as that. Now we will see mathematical analysis. So in mathematical analysis, what we actually do is we actually measure the ID current, okay, and actually measure the VGSQ. Practically we do it, okay, but to solve the problems, sometimes these values are given so that you can find the actual ID. If this is given, you find ID. If ID is given, you find VGS. Fine. Now here we call this as output section. Okay, you can see this as output section and this as input section. Fine. Now in this output section, you come from the higher voltage to the lower voltage. Okay, that is high potential to low potential. You move in that direction, and that is your KVL. So here, fine, this is minus VDD because you are exiting positive. So here if it is positive, it means it is like this. So you are coming in this direction, so you are entering negative, exiting positive. It means this is plus, and here there is a drop. Sorry, pardon. Here you are exiting positive, entering negative. It means it is a negative direction, that is negative symbol. Here you are entering positive, and here also you are entering positive. So this is VDS. So since you are entering positive for this ID into RD, which is an voltage drop, and this is an VDS. So simplifying, sending the other quantities, the VDS is required, keep it in left hand side, sending the other quantities, you will get this equation. So here for mathematical analysis, you just have to take KVL for output section and KVL for input section. That's it. Once you get those equations, you just simply substitute the values given, you will get the answer. That is how the problem is solved. Now you can see that Vs, that is source, is connected to ground. So obviously Vs is this, which is connected to ground, has to be 0 volts. Now we also know that VDS, we have this equation to solve, or we also have VDS is nothing but VD minus Vs. This is the convention always, correct? If you want VGS, you simply have to write VG minus Vs. This is how it is. G to S means G to S. So the way we have come from, okay, VDD to positive to ground is the same thing. This is higher potential to lower potential. Why? Because current flows like this, higher potential to lower potential. So VDS is equal to VD minus Vs. We already have seen Vs is 0 volts. So what is VD? You have measured this, correct? You have measured this. See here, you can actually measure, or you have got it from this equation. Of course we are not measuring, we are measuring VGS here, we are not measuring VDS, but here we have got it from this equation, right? Writing KVL to the outer loop output section, we have got VDS, so substitute that value. Okay, Vs is known, Vd is unknown, so you get relation. Okay, it means what? Vd is this point, this is Vd. Vd means what? From drain to, this is the drain, right? Drain, source and gate. So Vd means from there to ground. VDS means from drain to source. Vd, you got it. Since source is 0, this point is 0 here, so Vd is nothing but this drop. There is no drop here because there is no element or resistance or any other thing connected here. So ground is shorted here, this is a wire, so shorted, so ground is appearing here. It means there is only one drop, that is VDS, so VD becomes VDS. Similarly, as I said, VGS, you have VG minus Vs. This is unknown, this is known because you have measured it. Okay, Vs is 0, so you have this equation. So as I said, analysis is very simple, mathematical derivations is very simple. So if you are asked in exam, derive the equations for fixed bias FET, then you need to write these equations. Just write KVL for input and KVL for output. That's it. So we'll see a problem related to this. As I said, this is the given circuit and IDSS and VP is given. So the 2 points to solve it graphically, these are the 2 points to solve it graphically is been given. So this is your VP, this is your IDSS, this is your ID, okay, in milliamp. You should always know that the current will come in milliamp because it is a very small current. Here these are the values given. So how will you solve VGSQ? We already know that it is minus VGG. Okay, as I said, here the drop is very less because current is small. It's not that resistance is small, resistance is high, but current is very less. See, since resistance is high, current is very less. If one of the quantity multiplying quantity is near to 0, it means voltage drop is near to 0. So whatever the voltage is occurring here will be appearing here. So that is minus 2 volts. We have already derived this, right? Here, true, fine. Now we have this equation. What all parameters they have given? IDQ is what you want. Okay, first we'll see mathematically and then we'll see graphically. So this is the equation. IDSS is given, correct? VGS is given, VP is given. You substitute, you will get an answer 5.625 milliampere. And what is VDS? Is again got from the, see, VDS is not measured. Whatever you are measuring is current here and VGS. So this you have to calculate. And you write KVL equation for this. This is the KVL equation for outer loop. There are only 3 elements. One is rise, this is drop, and this is drop. So only 3 terms. So those 3 terms you write it, and you want VDS. You know VDD, you know ID, which you have calculated right now, and RD is also given. You substitute, you'll get it 4.75. And we also have seen that VD is nothing but VDS as ground is appearing here. Whatever the voltage is here is nothing but this voltage, correct? So VD means what? From drain to ground. What is VS? From source to ground. So this is VS, this is VD. And what is VDS? Between D to S, that is VD minus VS. If you do, you will get VDS. Whatever is VDS is same as VD, and VG is asked here. It is same as VGS, and VS you know that it is connected to ground, so that is 0 volts. So mathematically it is very simple. Graphically also it is very simple. Okay, you know that it is 10, and you know that this is minus 8 because it is given. Okay, so graphical approach, you got these 2 points, and VGS is minus 2 volts, right? VGS is minus 2 volt. This is VGS, which is nothing but VGG actually, but VGS is minus of that. So VGS is minus of this, so it is minus 2 volt. You draw a straight line, so wherever it intersects, okay, you can see here VP by 2, if you do, which is VP is 8, so minus 8 by 2 is minus 4. So for that you will get almost IDSS by 4. So for this is the current. So graphically when you plot, it is almost near to 5.6 milliampere, which we have got it here. Here this is approximate and this is actual. So graphically is also simple, very simple actually. In fact, it is simple because it is fixed bias. For other cases it may not be so easy, and mathematically also it is very easy for fixed bias. So hope you have understood, and I request you to pause this video at some point and conceptualize or visualize and rethink on your own so that you understand. And any doubts, any questions, you can please comment on the video. I'll be certainly responding to it. So that's it. Thank you.